so for chapter 8 we have some problems for current mirrors, and in this particular problem 8.1 we have this circuit that's a current mirror, and it's given that VDD is 1.3 volts and the reference current is 100 microamperes, and the output current that's been synced, it's 100 microamperes. And in part A we need to calculate what the value of R, that based on some specifications for the NMOS transistors here, would gives us that I out equals to 100 microamperes. Okay, so one thing is that we know that the resistance is for this circuit here is VDD minus VGS divided by ID1. Okay, and we also know that because there's no current flowing here at the base of the transistors, the reference current is actually equals to ID1, right? Because if I reference reaches this node, nothing goes here. So it basically means that ID1 is equals to the reference current. We know that we can calculate the current at flowing through the drain of an NMOS transistor using the exponential law. So if we assume that it's operating in the saturation mode, right, and that's required for this current mirror, we know that ID1 is equals to 1/2 of the process transconductance times the aspect ratio times the overdrive voltage squared, right? And remember that the overdrive voltage is VGS minus the threshold voltage. So one thing is that we know the length and width of the transistor, right? And we know the threshold voltage and the process transconductance. So we can calculate the overdrive voltage to determine the ground source voltage. That's the unknown that we have here, right? To define R. So if we isolate the overdrive voltage in this equation, the overdrive voltage is equals to the square root of 2 times ID1 divided by the process transconductance times the ratio, the aspect ratio, and that's it, right? So if we substitute the values for in this equation here, we get the overdrive voltage equals to the square root of 2 times ID1. Remember, it's the reference current, so it's 100, so 2 times 100 microamperes, divided by the process transconductance, that is 500 microamperes per volt squared, times the aspect ratio, which is 5 divided by 0.5. 5 micrometers for the width and 0.5 for the length. And let me just redraw this square root here. So it's the square root of this entire thing here. And this gives us an overdrive voltage of 0.2 volts. Okay, so if we know the overdrive voltage, we can calculate VGS. So VGS is just the overdrive voltage plus the threshold voltage. Now the threshold voltage we know for this particular transistor, that's 0.4. So this gives us 0.2 plus 0.4, and that's 0.6 volts for VGS. Since we know VGS, we know VDD, and we know ID1, we can calculate R. So R in this case is 1.3 VDD minus VGS, 0.6, divided by ID1. And remember, ID1 here is the same, ID1 here is the same as the reference current, right? So the reference current is 100 microamperes. And this gives us 7K ohms. Okay, so that's the answer for the first part. Okay, so basically if we set up this R to be 7k ohm, we have a current I naught that is 100 micro amperes. I'm not, well, that's true because they have like the same aspect ratio. Okay, so B, part B, what's the minimum value of V naught? So one thing, for this current mirror to operate, we must operate the NMOS transistors in the saturation mode. And for that, we must have V out that is greater or equals to VGS minus VT. And that's particular the overdrive voltage. So the minimum value that we have for V out is the overdrive voltage, which in our case is those 0.2 volts. Okay, so if V out goes below that 0.2 volts, then the NMOS, it stops working in the saturation region, and then it doesn't work anymore. It no longer works as a current mirror. Now for part C, we have an early voltage per micrometer of 5 volts, and we need to define what's the output current source, okay? Output resistance of the current source. So we know that the output resistance is just the early voltage divided by I naught, okay? And this means that we have this VA prime times the length of the transistor divided by I naught. That's the same as this 5 times the length, which is 0.5, divided by 100 micrometers. Okay, and this means that R out is equals to 25 kilo ohms. The last part, part D. So if we have a change in V out of 0.5 volts, what's the change in I naught? So we know that R out is equals to the change in voltage at the output divided by the change in the current. So if we isolate delta I naught here, that's the same as delta V naught divided by the output resistance. So if we have a change of 0.5 divided by those 25k ohms, this gives us a change in current that is 0.20 microamperes. Okay, so that's the solution for problem 8.1. Okay,